When we create 3D scenes, we use meshes composed by triangles like these ones, and to increase the realism of these objects, we can apply some kind of lighting and textures over their surfaces. But that's not enough. If we enlighten the surface of a plane with a brick's textures over it, this will appear immediately flat, and all the bumpy little depth details of the brick surface will not be considered. So, how can we solve this issue? What is the rendering technique that allows us to do so? This is the C++ 3D game tutorial series, and today we will see how normal mapping works. First of all, what is normal mapping? Normal mapping is a rendering technique that allows us to consider all the bumpy and little depth details of a particular surface when it is lit by a light source. In this moment, if we enlighten a plane of two triangles with a brick texture, the surface will appear immediately flat. That's because the lighting system doesn't find enough information about the little depth details of the surface. What kind of information we are talking about? The surface normals. Let's take again our brick wall. At the moment, we are using a flat plane composed by two triangles. So currently the lighting system considers only these 4 per vertex normals. However, these 4 normals are not enough to describe all the details about the brick wall. We will need further normals that describe each point of the brick surface. But how can we provide these further normals to the lighting system? The answer is through a texture, in particular through a particular texture called normal map. What is a normal map? As the name suggests, normal map is a map that contains information about normals of a particular surface, stored in RGB format. Let's see in detail how the normals are stored in the normal map. If we take a pixel of the map, and in particular its RGB color, we get 3 different values: the red color, the green color, and the blue color, that are the x, y, and z values of the normal vector respectively. With only a difference: the normal in RGB format is not the real normal. The values of the real normal have a range between -1 and 1. Instead, the values of the RGB normal have a range between 0 and 1. That means when we get the normal color, we have to transform it from the range 0, 1 to -1, 1 through the following formula. Very well. Now that we know how normals are stored and how to retrieve them, how can we use them to get the bumpy effects? We know that to enlighten our objects, a particular mathematical model is used in our pixel shader, the phone reflection model. We also know that this model needs the normal of a particular point of the surface to work. Perfect, so we have all the info we need, normals included. That's true, but we cannot use the normals obtained from normal map immediately. Why? Because the normals we get from a normal map are expressed in tangent space. The light direction and the other vectors used in the phone model are, instead, in world space. So we need to find a way to convert the normal from tangent space to world space. But how? First of all, let's see what is the tangent space. Tangent space is that space where the vectors are relative or local to the surface of a triangle. That means the vectors will have always the same direction regardless the current direction of the surface of a specific triangle. Also, in this space, the normals always point roughly along the positive z-axis. That's why the normal map has a general blue tint most of the time. The variation of colors across the normal map represent normal vectors that change directions respect to the positive z-axis, giving a sense of depth to the texture. At this point, we have to find a way to transform those normal vectors from tangent space to world space. As we have already seen in the previous tutorials, we can change it from a coordinate space to another one through a transform matrix. In this case, we have to create a rotation matrix called TBN. Then, we have to multiply our normal retrieved from normal map with this TBN matrix, obtaining in this way the final normal in world space. But what is a TBN matrix? TBN stands for tangent, binormal, and normal, and as the name suggests, is a rotation matrix composed by the tangent, the binormal, and normal vectors in world space. Well, but what are the tangent, binormal, and normal vectors? They are the axes that describe the tangent space. Tangent is the x-axis, binormal is the y-axis, and the normal is the z-axis. Well, at the moment we have the normal vectors, that are the normals of the surface of our 3D objects that we get from the tiny OBJ loader and so from the OBJ file. But we don't have the tangent and binormal vectors. Let's see how to compute the tangent and binormal vectors. As we can see from the image, the direction of tangent and binormal vectors are aligned with the direction of the texture coordinates of the surface, so the u and v coordinates. Now let's put a triangle as reference. This triangle has 3 points, P0, P1 and P2, with the texture coordinates T0, T1 and T2 respectively. Now let's define 2 edges of the triangles as E0 and E1. What can we do with this information? Let's take the edge 0, a vector that is the difference between P1 and P0. The texture coordinates differences of the edge 0, that we can call delta T0, are expressed in the same direction of the tangent and binormal vectors. Exploiting this aspect, edge 0 can be defined as the linear combination between tangent and binormal vectors. Let's see how linear combination works. If one vector is equal to the sum of scalar multiples of other vectors, it is said to be a linear combination of the other vectors. A vector is said scalar multiple if all its elements are multiplied by the same number. Good, that means E0 can be equivalent to the sum between a scalar multiple of tangent and the scalar multiple of binormal, where the scalar multiple of tangent is delta U0 multiplied by tangent, and the scalar multiple of binormal is delta B0 multiplied by binormal. Very well. The problem now is that these information are not enough to retrieve the tangent and binormal, so we have to take another edge and apply the same procedure. So let's take the edge 1. Perfect. We have all the information to retrieve tangent and binormal. So let's resolve these 2 equations. As first thing, let's expand the various vectors. At this point, these 2 equations can be resolved by writing them in matrix form. Good! Now, in order to get the tangent and binormal vectors, we have to simply divide the edges matrix with the delta t matrix. That means we have to make the inverse of the delta t matrix and multiply it with the edges matrix. Today we will not deepen how to calculate the inverse of a 2x2 matrix, but here is the final equation. By resolving this equation we get the tangent and binormal. Very well, we have everything we need to calculate our final normals. Let's see how to implement all of this concretely. As first thing, we add a compute tangents method in the mesh class with the following parameters. The 3 points P0, P1 and P2 and the three texture coordinates t0, t1, and t2 as input parameters, and then the tangent and binormal vectors as output parameters. Here we will place the equation we have just discussed. Then, in the mesh constructor, where we retrieve all the vertices of our object, we calculate the tangent and binormal per face. That's fine, but unfortunately we have to do something more. The normals we retrieve from obj file usually are calculated per vertex and not per face, but our tangents and binormal vectors are currently calculated per face. So let's see an example. Let's suppose our normals are calculated per face. We will have something like this. In this case, our tangents vectors will be fine, but since our normals are calculated per vertex, we have something like this. In this case, our tangents don't fit anymore. That means we have to reorient our tangents vectors in such a way to be orthogonal with the normal. This can be done with a very useful function called cross product. In few words, cross product allows to get a vector that is perpendicular for two given vectors. Good, how can we use this function to reorient our tangent vectors? As first thing, we can make a cross product between the normal per vertex obtained from obj file and the tangent per face, obtaining a vector. Vector is the per vertex binormal, that now it's orthogonal with the per vertex normal. At this point, let's redo the same thing between the per vertex binormal and per vertex normal, obtaining the final per vertex tangent. Very well, now we have tangents, binormals, and normals calculated per vertex. Now we have to store those new vectors in our vertex buffer by defining a new vertex layout both in the vertex mesh class and in the input layout object of the vertex buffer. Once we have all the data defined in our buffer, we can retrieve them in our shaders. In the vertex shader, we will get the tangent, binormal, and normal, and we will put them in a 3x3 matrix, that is, the TBN matrix mentioned earlier, taking care to multiply each vector with the word matrix. Then, in the pixel shader, once we have retrieved and transformed our normal from the normal map, we will finally multiply it with the TBN matrix, obtaining the final normal in word space. At the end, we will substitute this final normal into the dot product of the diffuse and the specular lighting equations. This will be the final result. Very well, now we can start the implementation. Let's start by adding a new filter called band mapping demo. And let's add a new class and let's call it always band mapping demo. At this point, let's open the template header and C++ files from the templates folder. These files can be downloaded by clicking on the download link available in the video description. Let's copy the content of template app header and C++ files in the correspondent band mapping demo class files. At this point, we have to rename the class name across the two files, from template app to bump mapping demo. The quick find window can be accessed by pressing Ctrl F. In the end, let's include bump mapping demo in the main C++ file. Before to build our demo, let's fix an issue in the window class, in particular in the broadcast method. Here we have to call onUpdate method continuously, otherwise the rendering could stuck during the input events. Let's build our demo. Unfortunately, there is an error. Since the lerp function is defined globally and it is used in more than one C++ file, there is an error of symbol defined multiple times. To solve this issue, we can make our lerp function static. Good, our basic demo works. At this point, let's go to bump mapping demo header file, and here let's define a new texture called brick texture and a new material called brick material. In the onCreate method, let's create our texture and material. Let's remember to set Cool Mode to back face. In the end, in the render method, let's push the brick material in the material list. Let's see if it works. And it works. Obviously, we are not able to see any bumpy effects. So let's start to compute our tangent and binormal vectors. Let's go to mesh header file and let's add the compute tangents method as we have already seen in the introduction. Now, we have to implement our compute tangents method. Here we have to do nothing but implementing the final equation obtained during the introduction. Some operators are not defined yet in the vector 3D and 2D. Let's implement them. And let's remember to set the various methods constant, in such a way to be usable from constant objects. Once we retrieve the tangent vector, we have to normalize it. So let's implement a normalize method in the vector 3D class. Very well. At this point, let's compute our tangent and binormal vectors per face. Here, for each face, let's get its 3 vertices and 3 texture coordinates. Now we can finally compute the tangent vectors. As we have already seen in the introduction, we have to transform the tangent and binormal of the current phase in such a way to be orthogonal with the normal obtained from OBJ file that is computed per vertex and not per phase. Here we have to use the cross function. We can copy-paste it from the cross.txt file available in the templates folder. Good, now we have to update the vertex mesh class with the new tangent and binormal vectors. Let's pass our vectors in the constructor. Very well. Let's move on with the next step about the update of the input layout objects in the vertex buffer C++ file. As we have already done with the other attributes, let's add the tangent and binormal attributes, taking care to set the correct offset in bytes. Let's set them even in the vertex mesh layout shader file. At this point, it's the turn of shaders. Let's add a new feature and let's call it Dear Light Bump Mapping. Let's create two HLSL files called Dear Light Bump BS and Dear Light Bump PS. Remember to exclude these files from build. Now we have to copy-paste the content of directional light vertex and pixel shaders into our new files. Good! As first thing, let's change the vertex layout in the vertex shader by adding the tangent and binormal attributes. Then, in the output vertex layout, let's add a new 3x3 matrix attribute called TBN. In the VS main function, let's populate the TBN matrix. In the first row, we set the tangent vector in word space. In the second row, the binormal in word space. And in the third row, the normal vector. Here we have finished. Now let's move on to the pixel shader. Let's add even here the TBN matrix attribute. Then let's add a new texture and sampler slot for the normal map. At this point, in the PS main function, let's retrieve our normal from the normal map. Here we have to transform the normal from range 0, 1 to range -1, 1. And in the end, let's take this normal and let's transform it from tangent to workspace by multiplying it with the TBN matrix. Let's replace the normal just calculated in the dot product of diffuse light and in the reflect function of specular lighting. And even the pixel shader is ready. We can go to the bump mapping file and we can add the normal map of brick surface. In the brick material, let's use the shaders just written. And let's add the normal map, taking care to add it after the diffuse color texture. Let's see if it works, and it works. Let's see how it works with specular lighting. And it works even with specular lighting. There is only a little issue, for on the side of the surface which the light doesn't arrive, there are some little unwanted lighting effects. To get rid of these effects, in the pixel shader, we can calculate the dot product between the light direction and the normal of the surface of the object, and not the one retrieved from the normal map. With this dot product, we can know if we are in the dark side or in the light side. If the dot product is greater than 0, we are in the light side. And exactly in this case we calculate the amount of specular lighting. Otherwise we set 0. Let's see if it works, and it works. That's all for now, folks. Today we have seen how normal mapping works and how to implement it. I hope you enjoyed this video. See you soon. Thanks for watching.